Millions, billions, or trillions? When it comes to the number of galaxies in our universe, the answer might just break your brain. Our own Milky Way is home to somewhere between 200 billion and 400 billion stars. That number alone is almost impossible to picture. But here's the thing. The Milky Way is just one galaxy, and out there, in the endless darkness of space, there are so many more galaxies that the total number has been a mystery for centuries. So how many galaxies are really out there? And why did scientists keep getting the answer wrong for so long? To understand how we got to our current best guess, we need to go back in time, way back, to an age when humans looked up at the night sky and had no idea what they were really seeing. For most of human history, people thought the universe was small. They believed that everything in the sky revolved around the Earth. The stars were just tiny points of light, maybe holes in a dark curtain that let the glow of heaven shine through. The idea that those stars could be other suns, far away and massive, was beyond imagination. It was not until the invention of the telescope in the early 1600s that everything started to change. Galileo Galilei pointed his simple telescope at the night sky and saw things no human had ever seen before. He saw craters on the moon, he saw moons orbiting Jupiter. And when he looked at the Milky Way, that faint band of light stretching across the sky, he saw something amazing. It was not a cloud or a mist. It was made up of countless individual stars packed so close together that they blurred into a river of light. This was the first hint that the universe was much bigger than anyone had imagined. But even Galileo did not know the true scale of what he was seeing. He had no way of knowing that those stars were part of an enormous spinning disk of matter, a galaxy. And he certainly had no idea that there were other galaxies out there, each one filled with billions of stars of its own. For the next few centuries, astronomers made slow progress. They mapped the stars, they measured distances. They built bigger and better telescopes, but one question kept bugging them. What were those fuzzy patches of light scattered across the sky? Some of them looked like smeared stars. Others looked like faint spirals or ovals. Astronomers called them nebulae, which is Latin for clouds. But no one knew what they really were. Some scientists thought the nebulae were just clouds of gas and dust inside our own galaxy. Others had a much bolder idea. They wondered if some of those fuzzy patches might actually be entire galaxies far, far away. Island universes, they called them. Collections of stars so distant that they appeared as nothing more than faint smudges of light. This debate raged for over 100 years. And it came to a head in 1920 in one of the most famous showdowns in the history of science. It is often called the Great Debate, and it took place at the Smithsonian Museum of Natural History in Washington, D.C. On one side was Harlow Shapley, a respected astronomer who believed that the Milky Way was basically the entire universe. He thought those fuzzy nebulae were just nearby clouds of gas, part of our own galaxy. On the other side was Haber Curtis, who argued that at least some of the nebulae were actually distant galaxies separate from the Milky Way and incredibly far away. Neither man could prove his case beyond a doubt. They did not have the technology to settle the argument. But the debate set the stage for one of the greatest discoveries in human history. And that discovery came just a few years later, thanks to a man named Edwin Hubble. Edwin Hubble was working at the Mount Wilson Observatory in California, using what was then the largest telescope in the world. It was called the Hooker telescope, and its mirror was 100 inches across. With this powerful instrument, Hubble turned his attention to a fuzzy patch of light known as the Andromeda Nebula. And what he found changed everything. Hubble spotted special stars called Cepheid variables in the Andromeda Nebula. Cepheid variables are stars that pulse in brightness in a very regular pattern. And astronomers had figured out a neat trick. The speed of a Cepheid's pulse is directly related to how bright the star really is. By measuring how fast a Cepheid pulses and how dim it appears from Earth, you can calculate how far away it is. When Hubble did the math, he got a number that was almost beyond belief. The Andromeda Nebula was not a cloud inside the Milky Way. It was a separate galaxy about 2 million light-years away. To put that in perspective, light travels at about 186,000 miles per second. A light year is the distance light travels in one full year, So 2 million light years is a distance so vast that it takes light 2 million years just to make the trip. This was a game changer. Suddenly, the universe was not just our little Milky Way. It was a vast ocean of galaxies, each one an island of stars separated by unimaginable distances. The great debate was over. Curtis had been right. And astronomers now had to face a new question. If there were other galaxies out there, how many were there? At first, the answer seemed modest. Astronomers could only see the galaxies that were bright enough and close enough to detect with their telescopes. Early estimates suggested there might be a few thousand galaxies in the observable universe. Then, as telescopes got better, the number climbed. Tens of thousands, hundreds of thousands. By the middle of the 20th century, some astronomers thought there might be millions of galaxies out there. But the biggest leap forward was yet to come. And it would arrive thanks to a telescope that floated high above the blurring effects of Earth's atmosphere. A telescope that could see deeper into space than anything that had come before. The Hubble Space Telescope. Launched in 1990, the Hubble Space Telescope was named after Edwin Hubble, the man who proved the existence of other galaxies. The telescope orbits about 340 miles above the Earth, where it can take incredibly sharp images without the distortion caused by our atmosphere. It was designed to peer into the deepest reaches of the cosmos and show us things we had never seen before. In 1995, astronomers decided to try something bold. They pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky near the Big Dipper. This little spot looked completely dark from Earth. There were no bright stars or known galaxies in that direction. It seemed like the most boring place to look. But they let the telescope stare at that spot for 10 straight days, slowly gathering light from the faintest and most distant objects. And when they finally processed the image, they were stunned. That tiny patch of sky was not empty at all. It was packed with galaxies. Nearly 3,000 of them, crammed into an area of sky smaller than a grain of sand held at arm's length. This image became known as the Hubble Deep Field, and it remains one of the most important photographs ever taken. It showed that no matter where you look in the sky, space is full of galaxies, and most of those galaxies are incredibly far away. Some of the light captured in that image had been traveling for billions of years before it reached the telescope. We were seeing galaxies as they were when the universe was young. The Hubble Deep Field forced scientists to completely rethink their estimates. If that one tiny patch of sky contained thousands of galaxies, then the whole sky must contain far more than anyone had guessed. Astronomers did the math. They took the number of galaxies in the deep field and multiplied it by the number of similar patches needed to cover the entire sky. The result was staggering. There were not millions of galaxies in the observable universe. There were at least 100 billion galaxies. Let that sink in for a moment. Each galaxy contains billions of stars. Each star might have planets. And there are 100 billion of these star cities scattered across the cosmos. The universe had just gotten a whole lot bigger in our minds. But wait, the story does not end there. As powerful as the Hubble Space Telescope was, it still had limits. It could only see galaxies that were bright enough or close enough to detect. What about the galaxies that were too faint? What about the tiny galaxies, or the ones that were so far away that their light had stretched and dimmed beyond what Hubble could pick up? In the years after the Hubble Deep Field, astronomers kept refining their estimates. They took follow-up images called the Hubble Ultra Deep Field and the Hubble Extreme Deep Field, staring at the same patch of sky for even longer periods. These images revealed even more galaxies, fainter and more distant than before. But scientists realized that even these incredible images were only showing part of the picture. The problem is that the early universe was a very different place. Galaxies were smaller back then. They had not yet merged and grown into the large spirals and ellipticals we see today. Many of those early galaxies were dim, tiny, and scattered. And as the universe has expanded, the light from those distant galaxies has been stretched into wavelengths that visible light telescopes like Hubble cannot easily see. So in 2016, a team of astronomers published a paper that rocked the scientific world. They used mathematical models and simulations to estimate how many galaxies might be hiding in the darkness, beyond what our telescopes could detect. Their conclusion was that the universe contained not 100 billion galaxies, but at least 2 trillion. 2 trillion galaxies. That is 2 followed by 12 zeros. It is a number so big that it is almost meaningless to the human brain. If you tried to count to 2 trillion, one number per second, it would take you over 63,000 years. And every single one of those galaxies is a vast collection of stars, gas, dust, and dark matter spinning through the void of space. This new estimate was based on the idea that the early universe was filled with many small galaxies that have since merged together. When galaxies collide, they do not pass through each other like ghosts. Their gravity pulls them together, and over millions or billions of years, they combine into larger galaxies. The Milky Way itself has swallowed up dozens of smaller galaxies over its long history, and it is currently on a collision course with the Andromeda Galaxy. In about 4.5 billion years, the two galaxies will merge into one giant galaxy, sometimes jokingly called Milkomeda. So when scientists say there are 2 trillion galaxies, they are talking about a kind of average over the history of the universe. If you could somehow see the universe as it was billions of years ago, you would see far more galaxies than you would today. Many of those ancient galaxies have since combined, reducing the total number. But the estimate of 2 trillion includes all. Those early galaxies, plus the ones that still exist today. Now, you might be wondering how confident scientists really are about this number. After all, we are talking about objects that are incredibly far away and incredibly faint. The honest answer is that 2 trillion is a best guess, not a final count. The true number could be higher or lower, depending on factors we do not fully understand yet. For example, there might be whole populations of galaxies that are so dim and so small that we have never detected them. These ultra-faint dwarf galaxies could be lurking in the darkness, outnumbering the big spirals and ellipticals that dominate our images. Some scientists think the real number of galaxies could be even higher than 2 trillion. On the other hand, our models of galaxy formation might be wrong. In some way, maybe galaxies merge faster than we think, or maybe there were fewer small galaxies in the early universe. In that case, the true number could be lower. The point is that 2 trillion is not a hard fact. It is the best estimate we can make with the data and tools we have right now. And speaking of tools, things are about to get very interesting. Because humanity has just launched a new telescope that can see farther and clearer than Hubble ever could. The James Webb Space Telescope, which began sending back images in 2022, is designed to observe the universe in infrared light. This is exactly the kind of light that gets stretched as it travels across the expanding universe. The James Webb Space Telescope can see galaxies that formed just a few 100 million years after the Big Bang. These are some of the first galaxies that ever existed, and they hold clues about how the universe evolved over billions of years. Early observations from Webb have already shown galaxies that are surprisingly bright and surprisingly mature for their age, suggesting that the early universe was more active than we thought. As Webb continues its mission, it will help astronomers refine the estimate of 2 trillion galaxies. It might confirm that number, or it might reveal that the true count is even higher. Either way, our understanding of the cosmos is about to take another giant leap forward. But here is the really mind-bending part. Everything we have talked about so far applies only to the observable universe. That is the region of space from which light has had time to reach us since the Big Bang. The observable universe is a sphere centered on Earth, about 93 billion light-years across. It is enormous by any human standard, but it is almost certainly not the whole universe. Think about it this way. The universe began with the Big Bang about 13.8 billion years ago. Since then, light has been traveling outward from all the stars and galaxies that formed. The farthest light we can see has been traveling for almost 13.8 billion years. But here is the catch. The universe has been expanding the whole time. The space itself has been stretching, carrying galaxies along with it. So even though the light has been traveling for 13.8 billion years, the objects that emitted that light are now much farther away than 13.8 billion light-years. That is why the observable universe is 93 billion light-years across, even though the universe is only 13.8 billion years old. It is also why we can never see beyond a certain distance. There are parts of the universe where light simply has not had enough time to reach us. And as the universe keeps expanding, there are regions that are moving away from us faster than the speed of light. We will never be able to see them, no matter how long we wait or how powerful our telescopes become. This means that the 2 trillion galaxies we have been talking about are just the ones in the observable universe. Beyond the edge of what we can see, there could be many, many more. How many more? That is where things get really wild. The truth is, we do not know how big the total universe is. Some scientists think it might be infinite. If the universe is truly infinite, then it contains an infinite number of galaxies, not just trillions, but an endless count that goes on forever. Every part of an infinite universe looks roughly the same as every other part, with galaxies scattered throughout. And since infinity has no end, the number of galaxies has no end either. But even if the universe is not infinite, it could still be much, much larger than the observable part. Some estimates suggest the total universe could be at least 250 times larger than the observable universe in terms of volume. If that is true, then the total number of galaxies could be in the hundreds of trillions or even quadrillions. Of course, these are just guesses. We have no way to measure what lies beyond the observable universe. We can only make assumptions based on the physics we understand. And physics tells us that the universe probably looks pretty much the same everywhere. If that is true, then wherever there is space, there are probably galaxies. This brings up a question that has haunted scientists and philosophers for centuries. Why is the universe so big? Why are there so many galaxies, so many stars, so many planets? What is the point of all that space? There is no easy answer to this question. Some people find it humbling. They look at the vastness of the cosmos and feel small, like a tiny speck in an endless ocean. Others find it exhilarating. They see all those galaxies as possibilities, as places where life might exist, where civilizations might rise and fall, where wonders beyond imagination might be waiting to be discovered. And then there is the mystery of dark matter and dark energy. These invisible forces make up most of the universe, yet we barely understand them. Dark matter provides the gravity that holds galaxies together. Without it, the stars in a galaxy would fly apart. But we have never directly detected dark matter. We only know it exists because of the way it affects the motion of stars and galaxies. Dark energy is even stranger. It is the force that is causing the expansion of the universe to speed up over time. Instead of slowing down due to gravity, the universe is expanding faster and faster, and no one knows why. Dark energy makes up about 68% of the total energy in the universe. Dark matter makes up about 27%. And everything else, all the stars, planets, gas, and dust that we can actually see, makes up less than 5%. So when we talk about 2 trillion galaxies, we are really only talking about the visible part of the cosmos, the part we can detect with our telescopes. The vast majority of the universe is made of stuff we cannot see and do not understand. It is a humbling reminder that even with all our knowledge and technology, we have only scratched the surface of what is out there. Let us take a moment to appreciate just how far we have come. A few hundred years ago, humans thought the universe consisted of the Earth, the Sun, the Moon, and a few thousand visible stars. We had no idea that galaxies existed. We had no concept of the true scale of the cosmos. Then came the telescope, and suddenly the universe grew. We discovered that the Milky Way was a galaxy, a vast island of hundreds of billions of stars. We learned that the fuzzy patches in the sky were other galaxies, millions of light years away. We realized that the universe was not small and cozy. It was vast, beyond comprehension. And the more we looked, the more galaxies we found. Thousands, millions, billions. And now, the best estimate says there are at least 2 trillion galaxies in the observable universe alone. Each one is a unique collection of stars, planets, and possibilities. Each one has its own history, its own shape, its own story. Some galaxies are spirals, like our Milky Way, with graceful arms sweeping outward from a bright central core. Others are ellipticals, smooth and rounded, filled with old red stars. Some are irregulars, with no clear shape at all, just chaotic swirls of stars and gas. And then there are the strangest ones, the ones that are merging with their neighbors, their shapes distorted by gravity into long tails and bridges of stars. Every type of galaxy exists in the 2 trillion total. every size, every color, every stage of life. Some are being born right now, collapsing out of clouds of gas in distant corners of the cosmos. Others are ancient, their stars burning low after billions of years. Some are violent, with supermassive black holes at their centers that swallow matter and blast out jets of energy. Others are quiet, drifting peacefully through the void. And here is something to think about. Almost every large galaxy has a supermassive black hole at its center. These black holes can have masses millions or billions of times greater than our Sun. The black hole at the center of the Milky Way is called Sagittarius A star, and it has a mass of about 4 million suns. But some galaxies have black holes that make ours look tiny. The black hole at the center of the galaxy M87 has a mass of about 6.5 billion suns. We have even taken a picture of it thanks to a worldwide network of radio telescopes called the Event Horizon Telescope. So when we say there are 2 trillion galaxies, we are also saying there are probably at least 2 trillion supermassive black holes, 2 trillion invisible monsters, each one warping space and time around it, each one a mystery wrapped in an enigma. And what about planets? If each galaxy has billions of stars, and many of those stars have planets, then the total number of planets in the observable universe is beyond calculation. We are talking about numbers with dozens of zeros, trillions upon trillions upon trillions of worlds, orbiting trillions upon trillions of stars in trillions of galaxies. The odds that Earth is the only planet with life suddenly seem very small. This is one of the reasons why the search for extraterrestrial life has become so important to scientists. With so many planets out there, the chances that some of them harbor life, maybe even intelligent life, seem almost certain from a statistical point of view. Of course, we have not found any evidence of alien life yet, but the search is still young, and the universe is very, very big. We have sent spacecraft to Mars and the moons of Jupiter and Saturn looking for signs of microbial life. We have built giant radio telescopes to listen for signals from distant civilizations. We have discovered thousands of exoplanets, worlds orbiting other stars, some of them in the habitable zone where liquid water could exist. Each discovery brings us closer to answering the ultimate question: are we alone? The sheer number of galaxies suggests that we probably are not, but until we find proof, we cannot be sure. And that uncertainty is part of what makes the cosmos so fascinating. It is a mystery that spans the entire universe, from the smallest particles to the largest structures. Speaking of structures, galaxies do not exist in isolation. They are grouped together by gravity into larger and larger collections. The smallest groupings are called galaxy groups, which contain just a few dozen galaxies. Our Milky Way is part of a galaxy group called the Local Group, which contains about 80 galaxies, including Andromeda and several smaller companions. Beyond groups are galaxy clusters, which contain hundreds or even thousands of galaxies. The nearest large cluster to us is the Virgo cluster, about 54 million light-years away. It contains over 1,000 galaxies and has a total mass of about 1,000 trillion suns. And even clusters are not the largest structures. Clusters are grouped into superclusters, which stretch across hundreds of millions of light-years. Our local group is part of the Laniakea supercluster, which contains about 100,000 galaxies spread over 500 million light-years. The name Laniakea comes from Hawaiian and means immense heaven. But even superclusters are just threads in a much larger web. When astronomers map the positions of galaxies across the observable universe, they find that galaxies are not scattered randomly. They are arranged in a vast cosmic web, with long filaments of galaxies separated by enormous voids of nearly empty space. The filaments look like the threads of a spider web, stretching and connecting across billions of light years, and the voids are gigantic bubbles of darkness containing almost no galaxies at all. This cosmic web is the largest structure in the known universe. It is shaped by gravity and dark matter, which together pull galaxies toward each other and form the filaments. The structure is so big that light takes billions of years to cross from one side to the other, and within this web, those 2 trillion galaxies are scattered like glowing beads on an immense tapestry. Understanding the cosmic web helps us understand how the universe evolved. In the beginning, right after the Big Bang, the universe was almost perfectly smooth. There were tiny ripples in the density of matter, but overall, everything was spread out evenly. Over billions of years, gravity amplified those tiny ripples. Regions with slightly more matter pulled in more and more, while regions with less matter emptied out. The result is the cosmic web we see today. The densest regions became galaxy clusters and superclusters. The emptiest regions became the voids. And connecting everything are the filaments, rivers of galaxies flowing through the darkness. It is a beautiful picture, and it is backed up by observations and computer simulations. Scientists have run simulations of the universe starting from the Big Bang and watched as virtual galaxies formed, merged, and arranged themselves into a cosmic web. The simulations match what we see in the real universe remarkably well. It is a stunning confirmation that we understand at least some of the basic physics that shape the cosmos. But there is still so much we do not know. We do not know why there is something rather than nothing. We do not know what dark matter is made of or why dark energy exists. We do not know if the universe is truly infinite or if there are other universes beyond our own. We do not know if life exists anywhere else or if we are truly alone. What we do know is that the universe is unimaginably vast and incredibly old. 14 billion years of history, trillions of galaxies, countless stars and planets, and all of it governed by the same laws of physics that we study here on Earth. The same gravity that makes an apple fall from a tree also holds galaxies together and shapes the cosmic web. That connection is one of the most profound ideas in all of science. The universe is not random, it follows rules. And those rules are the same everywhere, from the surface of Earth to the most distant galaxy visible in our telescopes. When we study physics and astronomy, we are reading the instruction manual of the cosmos itself. Now let us return to the question that started this whole journey. How many galaxies are there? We have gone from thinking there was only one galaxy, the Milky Way, to realizing there are at least 2 trillion in the observable universe. But as we discussed, the observable universe is just the part we can see. The total universe might be much, much larger. It might even be infinite. So the best answer we can give right now is this. There are at least 2 trillion galaxies in the part of the universe we can observe. But the true number in the entire universe could be far higher. It could be so high that the word trillion seems small by comparison. And we may never know the exact count because much of the universe lies forever beyond our reach. That might seem frustrating, but I think it is also beautiful. The universe keeps secrets. No matter how much we learn, there is always more to discover. Every answer we find leads to new questions. And that is what makes science so exciting. We are explorers, pushing into the unknown, mapping the unmappable, counting the uncountable. Let us take a step back and think about what all of this means for us. Here we are, on a small rocky planet orbiting an average star in one spiral arm of one galaxy among trillions. We are tiny beyond comprehension. Our entire civilization is less than a speck in the vastness of space. And yet, we are here. We exist. We are conscious beings who can look up at the night sky and wonder about our place in the cosmos. We can build telescopes and spacecraft. We can write equations that describe the motion of galaxies. We can ask questions that no other species on Earth can ask. That is remarkable. In a universe that is mostly cold, dark, and empty, there is at least one place where matter has organized itself into living, thinking beings. Beings who can appreciate beauty, feel love, and ponder the mysteries of existence. That is not nothing. That might be the most important thing in the entire universe. Some people look at the vastness of space and feel insignificant. They see all those galaxies and think, what does it matter? We are so small, our lives are so short, the universe does not care about us. But I think that misses the point. Yes, the universe is big and we are small, but size is not the only measure of importance. A single act of kindness matters, even if it happens on a tiny planet in an obscure corner of the cosmos. A work of art matters, even if civilization will ever see it. Love matters, hope matters, curiosity matters, and here's another way to think about it. Out of all the matter in the universe, most of it is just floating in space, doing nothing interesting. Stars burn and die, galaxies spin and collide, but almost all of that matter is unconscious. It does not know it exists. It cannot wonder or dream or hope. We are different. We are the universe becoming aware of itself. We are matter that has woken up and started asking questions. That makes us special, even in a cosmos of trillions of galaxies. Now, I know this is getting philosophical, and you might be wondering what any of this has to do with the number of galaxies. But I think the two are connected. The sheer scale of the universe is what makes these questions so urgent. When you realize how big it all is, you cannot help but ask what it means. And there are no easy answers. Science can tell us how many galaxies there are, at least approximately. It can explain how they formed and how they will evolve. But science cannot tell us why the universe exists in the first place, or what we should do with our brief time in it. Those are questions for philosophy, for religion, for art, for each of us to answer in our own way. What I can tell you is that the universe is a place of endless wonder. Every time we think we have figured it out, we discover something new that blows our minds. The Hubble Deep Field, the 2 trillion galaxy estimate, the James Webb Space Telescope. Each discovery reminds us that we are just getting started, and there is so much more to come. In the next few decades, we will learn more about the universe than we have in all of human history. New telescopes will peer deeper into space. New probes will explore our solar system. New experiments will search for dark matter and try to understand dark energy. And maybe, just maybe, we will find evidence of life beyond Earth. Imagine what that would mean. Imagine knowing for certain that we are not alone, that somewhere out there on some distant world, orbiting some distant star in some distant galaxy, there are other thinking beings looking up at their own night sky and wondering about their place in the cosmos. It would be the greatest discovery in human history. And if we do not find evidence of life, that would be significant too. It would make our existence even more precious. It would mean that we are truly rare, perhaps unique, in a universe of trillions of galaxies. Either way, the search is worth it. Either way, the question matters. Let us talk a bit more about how astronomers actually count galaxies, because it is not as simple as pointing a telescope at the sky and adding up what you see. The universe is so vast that we can only sample tiny portions of it. We cannot look at every galaxy individually. There are just too many. Instead, astronomers use a technique called extrapolation. They pick small patches of sky, study them in great detail, and then estimate how many similar patches would cover the whole sky. If a tiny patch contains 1,000 galaxies and there are millions of similar patches, then you can multiply to get the total. This is how the Hubble Deep Field gave us our first estimate of hundreds of billions of galaxies. The patch was small, but the count was high. And when astronomers multiplied by the number of patches needed to cover the sky, they got a number in the hundreds of billions. But extrapolation has limits. It assumes that the patch you studied is representative of the whole universe. What if it is not? What if some parts of the sky have more galaxies and some have fewer? Astronomers try to account for this by studying multiple patches in different directions. But there is always some uncertainty. The 2 trillion estimate went a step further. It used mathematical models to predict how many galaxies we might be missing. These models were based on our understanding of how galaxies form and evolve. They suggested that the early universe was filled with many small, faint galaxies that have since merged into larger ones. By accounting for these hidden galaxies, the estimate jumped from hundreds of billions to 2 trillion. But models can be wrong. They are based on assumptions, and if those assumptions are incorrect, the results will be 2. That is why the 2 trillion figure is still considered an estimate, not a fact. It is the best guess we can make with current knowledge. Future observations, especially from the James Webb Space Telescope, will help us refine it. One thing that makes galaxy counting tricky is defining what counts as a galaxy in the first place. Most of the time, a galaxy is a gravitationally bound system of stars, gas, dust, and dark matter. It has to be big enough to hold itself together with its own gravity. But there are borderline cases. For example, what about dwarf galaxies? These are tiny galaxies with just a few million stars, compared to the hundreds of billions in a giant like the Milky Way. Dwarf galaxies are very common, and there might be far more of them than large galaxies. But they are hard to detect because they are so faint. If we counted every tiny dwarf galaxy, the total number would go up. Then there are irregular galaxies, which do not have a clear shape. Some of these are the result of galaxy collisions, where two galaxies have smashed together and are in the process of merging. Should we count them as one galaxy or two? It depends on how far along the merger is, and what about the cores of galaxies that have been stripped of their outer stars by gravitational interactions? These leftover cores, called compact ellipticals or ultra-compact dwarfs, are tiny but dense. Do they count as galaxies, or are they something else? These definitional questions might seem trivial, but they actually matter when you are trying to count to 2 trillion. Different astronomers might give slightly different answers depending on how they define a galaxy. And as our telescopes get better and we discover more unusual objects, the boundaries will get even blurrier. Despite these challenges, the overall picture is clear. The universe is full of galaxies. Whether the exact number is 1 trillion, 2 trillion, or 10 trillion, the point is the same. We live in a cosmos of almost unimaginable richness and diversity. Let us now think about time as well as space. The light from distant galaxies takes a long time to reach us. When we look at a galaxy that is 1 billion light years away, we are seeing it as it was 1 billion years ago. The farther we look, the further back in time we see. This means that our telescopes are also time machines. When the James Webb Space Telescope observes a galaxy that formed just a few 100 million years after the Big Bang, it is showing us the universe as it was over 13 billion years ago. We are literally watching history unfold. And here's the thing. The universe has changed a lot over those 13 billion years. In the early days, galaxies were smaller, more chaotic, and more numerous. They had not yet had time to merge and grow. As time passed, galaxies collided and combined, becoming the large spirals and ellipticals we see today. The number of galaxies has been shrinking over cosmic time, even as individual galaxies have been growing. This is why the 2 trillion estimate includes galaxies from throughout the history of the universe. It is not saying there are 2 trillion galaxies right now at this moment. It is saying that if you add up all the galaxies that have ever existed, including the ones that have since merged, you get about 2 trillion. Today, the number of distinct galaxies is probably lower, maybe around 200 billion or so. But the total count across all of cosmic time is much higher. It is a subtle but important distinction. The future of galaxies is just as interesting as their past. The universe is still expanding, and that expansion is speeding up thanks to dark energy. Eventually, the galaxies that are far away from us will be moving away faster than the speed of light. They will disappear from our view one by one as they cross the edge of the observable universe. Trillions of years from now, a distant descendant of humanity, if any survive that long, might look up at the night sky and see almost nothing. The other galaxies will have faded from view. Only our local group, the galaxies bound to us by gravity, will remain visible. And even they will eventually merge into one giant galaxy. This future galaxy will be a lonely island in an empty void. No other galaxies will be visible. The cosmic web will have been stretched. Beyond recognition, the universe will still be vast, but it will seem smaller because so much of it will be hidden. It is a melancholy thought, but also a reminder of how special our current era is. Right now, we can see trillions of galaxies. We can study the cosmic web. We can trace the history of the universe back to the Big Bang. Future generations might not have that privilege. The observable universe is actually shrinking over time, as more and more galaxies slip beyond the horizon. So in a way, we are living in a golden age of astronomy. We have the technology to see the cosmos in all its glory. We have the knowledge to understand what we are seeing. And we have the curiosity to keep pushing forward, to keep asking questions, to keep exploring. That is what makes this topic so exciting to me. The number of galaxies is not just a statistic, it is a window into the nature of reality. It tells us about the size and age of the universe. It tells us about the forces that shape the cosmos. It tells us about our own place in the grand scheme of things, and every new discovery changes the picture. A few decades ago, we thought there were maybe 100 billion galaxies. Now we think there are at least 2 trillion. Who knows what we will think in another few decades? Maybe the number will go up again. Maybe we will discover whole new types of galaxies that we never knew existed. Maybe we will find evidence that the universe is even larger than we imagined. That is the joy of science. It never stands still. It is always moving, always growing, always surprising us. And the universe is the ultimate laboratory, full of mysteries waiting to be solved. Now, before we wrap up, let me address one more question that might be on your mind. What about other universes? You might have heard of the multiverse, the idea that our universe is just one of many. If there are other universes, each with their own galaxies, then the total number of galaxies across all of reality would be even higher than anything we have discussed. The multiverse is a fascinating idea, but it is important to be honest about what we know and what we do not know. Right now, there is no direct evidence that other universes exist. The multiverse is a theoretical concept suggested by some versions of physics, but not confirmed by observation. We cannot see other universes or communicate with them. They are, by definition, beyond our reach. That does not mean the multiverse is impossible. It just means we should be careful about treating it as fact. It is an idea worth exploring, and many serious scientists take it seriously. But until we have evidence, it remains in the realm of speculation. For now, let us focus on what we can observe. The observable universe contains at least 2 trillion galaxies. That is already more than enough to boggle the mind. And as our tools improve, we will learn more and more about each of those galaxies, their histories, their structures, their secrets. Every galaxy is a story of gravity and gas, of stars being born and dying, of planets forming and orbiting, of cosmic drama playing out over billions of years, and we are just beginning to read those stories. Every image from the James Webb Space Telescope is a new chapter. Every scientific paper is a new page. The book of the universe is still being written, and we are lucky enough to be the readers. So the next time you look up at the night sky, remember what you are seeing. Those faint points of light are not just stars. Beyond them, scattered across the blackness, are trillions of galaxies. Each one is a city of stars. Each one is a world of wonders, and together they make up the vast, beautiful, mysterious cosmos that is our home. We are tiny, we are brief, but we are here. And we are curious. That curiosity has driven us to build telescopes and launch spacecraft. It has driven us to ask questions that seemed unanswerable. And bit by bit, we are finding answers. 2 trillion galaxies, maybe more, maybe far, far more. The universe is bigger than we ever dreamed, and we are still dreaming. Thank you for joining me on this journey through the cosmos. If you found this video interesting, please hit the like button and subscribe to the channel. We explore the wonders of the universe in every video, and there is always more to discover. I would love to know what you think. Do you believe the universe is infinite? Do you think there is life in those trillions of galaxies? Drop a comment below and share your thoughts. Until next time, keep looking up. But before you go, let me take you a little deeper, because there is so much more to explore. The story of galaxies is not just about counting them, it is about understanding them. And the more we understand, the more amazing the universe becomes. Let us start with something fundamental. What exactly is a galaxy? We have mentioned stars, gas, dust, and dark matter. But how do these ingredients come together to form the vast structures we see in our telescopes? It all begins with gravity. Gravity is the weakest of the 4 fundamental forces, but it is also the most far-reaching. Unlike the strong nuclear force or the electromagnetic force, gravity never stops. It reaches across the entire universe, pulling matter together. In the early universe, right after the Big Bang, matter was spread out almost evenly. Almost, but not quite. There were tiny ripples in the density, regions where matter was just slightly more concentrated than average. These ripples were the seeds of everything we see today. Over millions of years, gravity went to work. The regions with slightly more matter pulled in more matter from their surroundings. They grew denser and denser, while the regions with less matter grew emptier. Eventually, the dense regions collapsed into the first stars and the first galaxies. This process took hundreds of millions of years. For a long time after the Big Bang, the universe was dark. There were no stars yet, no galaxies, just clouds of hydrogen and helium gas drifting through space. This period is sometimes called the Cosmic Dark Ages. Then, around 200 million years after the Big Bang, the first stars ignited. These were not like the stars we see today. They were massive, hundreds of times, more massive than the sun, and they burned incredibly bright and hot. They lived fast and died young, exploding as supernovae after just a few million years. Those early supernovae were crucial for the evolution of the universe. When a star explodes, it scatters heavy elements into space, elements like carbon, oxygen, iron, and gold. These elements did not exist in the early universe. They were forged in the hearts of stars and spread by their deaths. The first galaxies formed around the same time as the first stars, or perhaps slightly later. They were small and chaotic, nothing like the elegant spirals and smooth ellipticals we see today. They were clumpy collections of stars, gas, and dark matter tumbling through space and colliding with each other. Those collisions were important. When two galaxies collide, they do not simply bounce off each other. Their gravity pulls them together, mixing their stars and gas. Over millions of years, they merge into a single, larger galaxy. This process of merging has been happening throughout the history of the universe. It is how small galaxies grew into large ones. The Milky Way is a good example. Our galaxy has swallowed up many smaller galaxies over its long lifetime. Some of those galaxies have been completely absorbed. Their stars scattered throughout the Milky Way. Others are still in the process of being consumed. The Sagittarius dwarf galaxy, for instance, is currently being torn apart by the Milky Way's gravity. Its stars are being stretched into long streams that wrap around our galaxy. And as we mentioned earlier, the Milky Way is on a collision course with the Andromeda Galaxy, F1. In about 4 to 5 billion years, the two galaxies will collide and merge. The collision will take hundreds of millions of years to complete. Stars will be flung into new orbits. Gas clouds will compress and trigger bursts of star formation. And eventually, the two spirals will settle into a single elliptical galaxy. Do not worry, though. Even though we call it a collision, individual stars are so far apart that actual collisions between stars will be extremely rare. Our solar system will probably survive the merger intact, though it might end up in a very different part of the new galaxy. Now let us talk about the different types of galaxies. Astronomers have classified galaxies into several main categories based on their shape. The most famous classification system was developed by Edwin Hubble, the same astronomer who proved that other galaxies exist. Hubble divided galaxies into three main types: elliptical galaxies, spiral galaxies, and irregular galaxies. This classification system is sometimes called the Hubble sequence or the Hubble tuning fork because of the way it is often drawn. Elliptical galaxies are smooth and rounded. They range from nearly spherical to elongated and cigar-shaped. They contain mostly old red stars and have very little gas and dust. Star formation in elliptical galaxies has largely stopped because there is no raw material left to make new stars. Elliptical galaxies are often the result of galaxy mergers. When two spiral galaxies collide, the orderly rotation of their disks is disrupted. Stars are scattered into random orbits, and the final result is an elliptical shape. Some of the largest galaxies in the universe are giant ellipticals containing trillions of stars. Spiral galaxies, like the Milky Way, have a flattened disk with spiral arms winding outward from a central bulge. The arms are regions of active star formation filled with young, hot blue stars. The spaces between the arms contain older, redder stars. Spiral galaxies also have a lot of gas and dust, which provides the raw material for new stars. The arms of a spiral galaxy are not solid structures. Stars do not stay in the arms forever. Instead, the arms are density waves, regions where stars bunch up temporarily before moving on. It is like a traffic jam on a highway. Cars enter the jam, slow down, and then speed up again on the other side. The jam itself does not move very fast, even though individual cars are passing through. There are also barred spiral galaxies, which have a bar-shaped structure running through the center. The Milky Way is actually a barred spiral. The bar is thought to influence the motion of stars and gas in the galaxy, and it may play a role in funneling material toward the central black hole. Irregular galaxies are the third major type. These galaxies do not fit neatly into the elliptical or spiral categories. They have chaotic, asymmetrical shapes, often caused by gravitational interactions with other galaxies. The Magellanic Clouds, two small galaxies that orbit the Milky Way, are irregular galaxies. They are visible from the southern hemisphere and have been known since ancient times. In addition to these main types, there are many subcategories and variations. Lenticular galaxies, for example, are somewhere between ellipticals and spirals. They have a disk but no spiral arms. Dwarf galaxies are much smaller than regular galaxies and come in various shapes. and peculiar galaxies have unusual features, often caused by ongoing collisions or interactions. One of the most dramatic types of galaxies is the starburst galaxy. These are galaxies that are forming stars at an incredibly high rate, much faster than the Milky Way. Starburst galaxies are often triggered by galaxy collisions, which compress gas clouds and spark rapid star formation. They are bright and energetic, but they cannot sustain their star formation for long. Eventually, they run out of gas and settle down. At the other extreme are the quiescent galaxies, which have almost completely stopped forming stars. These are usually elliptical galaxies or very old spirals. They are dominated by red, low-mass stars that burn slowly and live for a very long time. Without new star formation, these galaxies are gradually fading. Now let us talk about something that cannot be seen directly but is absolutely essential to galaxies. Dark matter. We mentioned it earlier, but it deserves a closer look, because without dark matter, galaxies as we know them would not exist. Dark matter is a mysterious substance that does not emit, absorb, or reflect light. We cannot see it with any telescope, but we know it exists because of its gravitational effects on visible matter. The first hints of dark matter came in the 1930s when astronomer Fritz Zwicky was studying the Coma cluster, a large cluster of galaxies about 300 million light-years away. Zwicky measured the speeds of galaxies in the cluster and found something strange. The galaxies were moving so fast that the cluster should have flown apart long ago. The visible matter in the cluster was not nearly enough to hold it together with gravity. Zwicky proposed that there must be some unseen matter providing the extra gravity. He called it dark matter. At the time, his idea was largely ignored. But decades later, more evidence emerged. In the 1970s, astronomer Vera Rubin studied the rotation of spiral galaxies. She measured how fast stars orbited around the center of each galaxy and plotted the results. According to the laws of gravity, stars far from the center should orbit more slowly than stars near the center, just as outer planets in our solar system orbit more slowly than inner planets. But Rubin found something unexpected. Stars at the outer edges of galaxies were orbiting just as fast as stars near the center. This was impossible unless there was a lot of unseen mass in the outer parts of the galaxy, providing extra gravity. The only explanation was dark matter, forming a vast halo around each galaxy. Since then, evidence for dark matter has piled up. We see its effects in the bending of light around galaxy clusters, a phenomenon called gravitational lensing. We see its imprint in the cosmic microwave background, the faint glow left over from the Big Bang. And our computer simulations of the universe only match observations if we include dark matter. Yet despite decades of searching, we have never directly detected a dark matter particle. We do not know what dark matter is made of. There are many theories. Weakly interacting massive particles, or WIMPs, are one popular candidate. Axions are another. But so far, all experiments designed to catch dark matter particles have come up empty. This is one of the biggest unsolved mysteries in physics. Dark matter makes up about 27% of the universe, far more than ordinary matter. And yet we do not know what it is. It is humbling to realize that most of the matter in the universe is invisible and unknown. But dark matter is not the only mystery. There is also dark energy, which is even stranger. Dark energy makes up about 68% of the universe, making it the dominant component. And unlike dark matter, which pulls things together with gravity, dark energy pushes things apart. The discovery of dark energy came in the late 1990s when two teams of astronomers were studying distant supernovae. These supernovae are useful because they all have about the same brightness, which means you can use them to measure distances. By comparing how bright a supernova appears to how bright it really is, you can figure out how far away it is. The two teams expected to find that the expansion of the universe was slowing down due to gravity. But they found the opposite. The expansion was speeding up. Distant galaxies were moving away from us faster than expected. Something was pushing them, counteracting gravity and accelerating the expansion. That something is dark energy. We do not know what it is or where it comes from. It might be a property of empty space itself, a kind of vacuum energy that permeates the cosmos. Or it might be something completely different. All we know is that it exists, and that it is making the universe expand faster over time. Dark energy has profound implications for the future of the universe. As the expansion accelerates, distant galaxies will move farther and farther away. Eventually, they will cross the cosmological horizon and disappear from our view. The observable universe will shrink even as the total universe keeps expanding. In the very far future, trillions of years from now, the universe might become a cold, dark, and lonely place. Stars will burn out, galaxies will fade, and intelligent beings, if any still exist, will see an almost empty sky. But that is far in the future. Right now, we live in a universe that is vibrant and full of light. 2 trillion galaxies are out there, each one a treasure trove of stars and secrets. And we are just beginning to explore them. Let us talk about some of the most extreme galaxies in the universe, because not all galaxies are calm and peaceful. Some are violent and dramatic, putting on shows that defy imagination. Active galactic nuclei, or AGN, are galaxies with supermassive black holes at their centers that are actively consuming material. As matter falls toward the black hole, it heats up and emits tremendous amounts of energy. An active galactic nucleus can outshine the entire rest of its galaxy. The most extreme type of AGN is a quasar. Quasars are so bright that they can be seen from billions of light years away. They look like points of light, almost like stars, which is why they were originally called quasi-stellar objects. But they are actually the cores of distant galaxies, powered by black holes with masses of millions or billions of suns. The first quasars were discovered in the 1960s, and astronomers were baffled. How could a point of light be so incredibly bright? The answer turned out to be the supermassive black hole, one of the most efficient energy converters in the universe. As matter spirals into a black hole, it releases about 10% of its mass as energy. That is far more efficient than nuclear fusion, which powers stars. Today, we know that many galaxies go through an active phase at some point in their history. When a lot of gas falls toward the central black hole, the galaxy lights up as a quasar or some other type of AGN. When the gas runs out, the activity dies down. The Milky Way's black hole is currently quiet, but it has probably been active in the past. Another extreme type of galaxy is the starburst galaxy, which we mentioned earlier. These galaxies are forming stars at an incredible rate, sometimes 100 times faster than the Milky Way. The intense star formation is usually triggered by a collision or interaction with another galaxy. One famous example is the Antennae galaxies, a pair of colliding galaxies about 60 million light-years away. The collision has triggered a massive burst of star formation, creating billions of new stars. Images of the Antennae galaxies show long tails of stars and gas that were flung out during the collision, giving the system its name. Starburst galaxies are important because they show us how galaxy collisions transform the cosmos. They are also visible from great distances because of their intense light output. This makes them useful for studying the early universe, when collisions and mergers were more common. On the other end of the spectrum are ultra-diffuse galaxies, which are surprisingly dim and spread out. These galaxies have the same number of stars as dwarf galaxies, but are spread over a much larger area. They are so faint that they were only discovered recently using advanced imaging techniques. Ultra-diffuse galaxies pose a puzzle. How did they form? Why are they so spread out? Some might be failed galaxies that never managed to collect enough gas to form many stars. Others might have been puffed up by violent events like multiple supernova explosions. The answers are still being debated. There are also ultra-compact dwarf galaxies, which are the opposite. These are tiny but extremely dense, with millions of stars packed into a small space. They might be the stripped cores of larger galaxies that lost their outer layers to gravitational interactions. And then there are the jellyfish galaxies, which are being stripped of their gas as they plunge through the hot gas of a galaxy cluster. Long tentacles of gas trail behind them, like the tentacles of a jellyfish. These galaxies are slowly being transformed as they lose the raw material for star formation. The variety of galaxies is truly astounding. No two are exactly alike. Each one has its own history, its own shape, its own character. Together they form a cosmic zoo of wonders, from giant ellipticals with trillions of stars to tiny dwarfs with just a few million. Let us now consider the biggest structures in the universe, the ones that contain galaxies as building blocks. We talked earlier about galaxy groups, clusters, superclusters, and the cosmic web, but there are some specific structures worth highlighting. The Virgo cluster is the nearest large cluster of galaxies to the Milky Way. It contains over 1,000 galaxies and lies at the center of the Virgo supercluster, which includes our local group. The gravity of the Virgo cluster is slowly pulling the local group toward it at a speed of about 200 miles per second. Even larger is the Laniakea supercluster, which was only defined in 2014. Laniakea contains about 100,000 galaxies, including the Milky Way, the local group, the Virgo cluster, and many other groups and clusters. It spans over 500 million light-years and contains about 100 million billion solar masses. The boundaries of Laniakea are defined by the flow of galaxies. Within Laniakea, galaxies are flowing toward a common center of gravity called the Great Attractor. Outside Laniakea, galaxies are flowing toward different centers. It is like watersheds on Earth, where water flows toward different rivers depending on which side of a ridge it lands. The Great Attractor is a mysterious region of space that has puzzled astronomers for decades. It is located in the direction of the constellation Centaurus, about 200 million light-years away. We cannot see it directly because it lies behind the disk of the Milky Way, obscured by dust and stars. But we know it is there because of its gravitational pull on nearby galaxies. For a long time, astronomers thought the Great Attractor was itself the ultimate destination. But recent studies have revealed an even larger structure beyond it. The Shapley supercluster, located about 650 million light-years away, contains thousands of galaxies and is one of the most massive concentrations of matter in the nearby universe. It might be the true center of attraction, with the Great Attractor just a way station on the journey. Beyond superclusters, the cosmic web stretches across the entire observable universe. Filaments of galaxies connect clusters like threads in a tapestry. Voids, some of them hundreds of millions of light-years across, separate the filaments. The whole structure looks like a sponge or a neural network with dense nodes connected by thin strands. The largest single structures in the cosmic web are called galaxy filaments or Great Walls. The Sloan Great Wall, discovered in 2003, is about 1.4 billion light-years long. The Hercules Corona Borealis Great Wall, discovered in 2013, might be even larger, stretching over 10 billion light-years. These structures are so vast that light takes billions of years to cross them. Yet even these great walls are dwarfed by the observable universe as a whole, 93 billion light-years across, containing at least 2 trillion galaxies, organized into a web of filaments and voids. It is the grandest structure we know of, and we are just one tiny part of it. How did astronomers map this cosmic web? It was not easy. Galaxies are scattered across the sky, and measuring their distances requires careful work. For each galaxy, astronomers had to determine both its position on the sky and its distance from Earth. Only then could they build a three-dimensional map. Distance measurements rely on a variety of techniques. For nearby galaxies, astronomers use Cepheid variable stars, the same method Edwin Hubble used to prove that Andromeda was outside the Milky Way. For more distant galaxies, they use supernovae, which can be seen from billions of light-years away, and for the most distant objects, they rely on the redshift of light. Redshift is caused by the expansion of the universe. As light travels through expanding space, its wavelength gets stretched. Blue light becomes redder. The more the universe has expanded during the light's journey, the greater the redshift. By measuring a galaxy's redshift, astronomers can estimate how far away it is. Large galaxy surveys, like the Sloan Digital Sky Survey, have measured the positions and redshifts of millions of galaxies. These surveys create detailed maps of the cosmic web, revealing its filaments and voids. They show us the large-scale structure of the universe in stunning detail. One surprising finding from these surveys is just how uniform the universe is on the largest scales. If you zoom out far enough, the cosmic web smooths out. The universe looks the same in every direction, roughly. This is called the cosmological principle, and it is a fundamental assumption of modern cosmology. The cosmological principle makes sense if the universe started from a nearly uniform state, as the Big Bang theory predicts. The tiny ripples in the early universe grew into the cosmic web, but on the largest scales, those ripples average out. The universe has no center and no edge. It is the same everywhere on average. This uniformity has profound implications. It means that the laws of physics are the same everywhere in the universe. An atom on the other side of the cosmos behaves just like an atom here on Earth. Gravity works the same way, whether you're in the Milky Way or in a galaxy 10 billion light years away. It also means that the universe has no special places. The Milky Way is not at the center of anything. We are just one galaxy among trillions, located in one corner of one filament of one supercluster. There is nothing particularly special about our location except that it is where we happen to be. This realization is both humbling and liberating. Humbling because it reminds us of our insignificance on the cosmic scale. Liberating because it means the entire universe is open to us. Wherever we look, we see the same physics, the same structures, the same possibilities. Now let us return to the question of how the number of galaxies might change in the future, not just because of mergers and new discoveries, but because of how we define and observe galaxies. As telescopes improve, we detect fainter and smaller objects. Some of these might be classified as galaxies, while others might be classified as something else. The boundary between a small galaxy and a large star cluster is not always clear. Both are collections of stars bound by gravity. But galaxies typically have their own dark matter halos, while star clusters do not. Future telescopes might discover populations of ultra-faint galaxies that we cannot see today. These tiny systems with just a few thousand stars might vastly outnumber the large galaxies we are familiar with. If we count them all, the total number of galaxies could go up significantly. On the other hand, our definition of a galaxy might become more restrictive. If we require a certain minimum mass or a certain amount of dark matter, then some objects currently classified as galaxies might be reclassified as something else. The number could go down. The point is that the count of 2 trillion galaxies is not a fixed truth. It is a snapshot of our current understanding based on current definitions and current technology. As those change, the number will change too. Science is a process, not a destination. Let us also think about the galaxies we cannot see, even with our best telescopes. The observable universe has a hard edge, the cosmological horizon, beyond which light has not had time to reach us. But the total universe extends beyond that edge. If the universe is infinite, as some models suggest, then it contains infinitely many galaxies. In that case, asking how many galaxies there are becomes meaningless. Infinity is not a number you can count to. It is a concept that defies ordinary arithmetic. If the universe is finite but very large, then the total number of galaxies is finite but enormous. It could be quadrillions or quintillions or even larger numbers that do not have common names. We simply do not know. What we do know is that the observable universe, the part we can study with telescopes, contains about 2 trillion galaxies. And that is already more than we can fully comprehend. 2 trillion is such a large number that it might as well be infinite for practical purposes. Consider this thought experiment. Imagine you wanted to visit every galaxy in the observable universe. Even if you could travel at the speed of light, which is impossible for anything with mass, it would take you billions of years just to reach the nearest galaxies. Reaching the most distant ones would take over 40 billion years. And remember, the universe is expanding. By the time you reached a distant galaxy, it would have moved even farther away. You would be chasing a receding target, and you could never catch up. The expansion of the universe sets a fundamental limit on how much of the cosmos we can ever explore. This is another reminder of how vast and impersonal the universe is. It was not designed for human exploration. It operates on scales of space and time that dwarf anything in our experience. And yet, from our tiny corner, we have managed to understand so much. That achievement is worth celebrating. Just a few centuries ago, humans did not know that other galaxies existed. Now we know there are trillions of them. We have mapped their shapes, studied their compositions, traced their histories. We have seen galaxies colliding, galaxies being born, galaxies dying. We have peered back in time to the earliest epochs of the universe. All of this knowledge came from human curiosity and ingenuity. We built telescopes and spacecraft. We developed theories and tested them. We made mistakes and corrected them. And step by step, we uncovered the secrets of the cosmos. That journey is far from over. The James Webb Space Telescope is just the beginning of a new era of discovery. Future telescopes will be even more powerful. They will see galaxies that are currently invisible. They will answer questions we have not yet thought to ask. And perhaps someday we will find evidence of life beyond Earth. That discovery, if it ever comes, would be the greatest in human history. It would confirm that we are not alone in this vast universe. It would change how we see ourselves and our place in the cosmos. For now, we can only wonder. Are there other civilizations out there gazing at their own night skies, asking the same questions we ask? Are there beings in distant galaxies who have figured out what dark matter is or why the universe exists at all? The possibilities are endless, literally. Let me share a few more facts that help illustrate the scale of what we are talking about. The Milky Way is about 100,000 light-years across. The Andromeda Galaxy is about 220,000 light-years across. The nearest large galaxy cluster, the Virgo cluster, is about 54 million light-years away. The edge of the observable universe is about 46 billion light-years away. These numbers are so large that they lose meaning, so let us try a different approach. Imagine the sun was shrunk to the size of a grain of sand. On this scale, the nearest star, Proxima Centauri, would be about 4 miles away. The Milky Way would be about 100,000 miles across, and the observable universe would be about 60 trillion miles across. That is still too big to imagine, but it gives some sense of the scale. Another way to think about it is in terms of time. Light from the sun takes about 8 minutes to reach Earth. Light from the nearest star takes about 4 years. Light from the center of the Milky Way takes about 26,000 years. Light from the Andromeda Galaxy takes about 2.5 million years. And light from the edge of the observable universe has been traveling for almost 14 billion years. When we look at distant galaxies, we are looking back in time. We see them as they were when their light left, not as they are now. A galaxy 10 billion light-years away is seen as it was 10 billion years ago. The universe we observe is really a mosaic of different times, with nearby objects showing recent history and distant objects showing ancient history. This is why the James Webb Space Telescope is so important. By seeing farther, it sees earlier. It can observe galaxies that formed just a few 100 million years after the Big Bang, showing us what the universe looked like in its infancy. Those early galaxies are very different from the galaxies we see nearby, giving us clues about how galaxies evolved over cosmic time. One of the surprises from Webb's early observations is that the early universe contained some unexpectedly large and bright galaxies. According to our models, galaxies should have been small and dim in the early universe, only growing large over billions of years. But Webb has found galaxies that seem too big and too bright for their age. This could mean that galaxies form faster than we thought, or it could mean that something else is going on, something we do not yet understand. Either way, it is a reminder that the universe often defies our expectations. Just when we think we have it figured out, it throws us a curveball. These surprises are what make astronomy so exciting. Every new telescope brings new puzzles. Every puzzle leads to new insights. And every insight brings us closer to understanding the cosmos. Let me also mention some of the technologies that make galaxy observation possible. Telescopes are the most obvious tool, but they have come a long way from Galileo's simple glass lenses. Modern telescopes use mirrors instead of lenses because mirrors can be made much larger without becoming too heavy. The Hubble Space Telescope has a mirror about 8 feet across. The James Webb Space Telescope has a mirror about 21 feet across, made of 18 hexagonal segments that unfold after launch. Ground-based telescopes can be even larger. The Very Large Telescope in Chile has 4 mirrors, each about 27 feet across, that can work together. The Extremely Large Telescope, currently under construction, will have a mirror over 130 feet across. It will be the largest optical telescope ever built. These giant mirrors collect more light, allowing them to see fainter objects. They also have better resolution, allowing them to see finer details. But ground-based telescopes have to deal with the blurring effects of Earth's atmosphere. They use a technology called adaptive optics, which measures atmospheric distortion in real time and adjusts the mirror to compensate. Space telescopes do not have this problem. Above the atmosphere, images are sharp and clear. But launching a telescope into space is expensive and difficult. The James Webb Space Telescope took over 20 years to develop and cost about $10 billion. Radio telescopes are another important tool for studying galaxies. They detect radio waves instead of visible light, which allows them to see things that optical telescopes cannot. Radio waves can penetrate dust clouds that block visible light. They can also reveal cold gas that does not emit visible light at all. The largest radio telescope in the world is the 500-meter Aperture Spherical Telescope, or FAST, in China. Its dish is about 1,600 feet across, making it the most sensitive radio telescope ever built. It can detect faint radio signals from the most distant corners of the universe. Radio telescopes can also be combined into arrays, with multiple dishes working together as a single instrument. The Very Large Array in New Mexico has 27 dishes spread over 13 miles. The Atacama Large Millimeter Array in Chile has 66 dishes. And the Event Horizon Telescope, which took the first picture of a black hole, links telescopes around the world into an Earth-sized array. Each type of telescope reveals different aspects of galaxies. Optical telescopes show stars and glowing gas. Infrared telescopes show warm dust and the light from distant red-shifted galaxies. Radio telescopes show cold gas and energetic jets from black holes. X-ray telescopes show the hottest gas in galaxy clusters. And gamma-ray telescopes show the most violent explosions in the universe. By combining observations from all these wavelengths, astronomers build a complete picture of each galaxy. It is like listening to an orchestra instead of just one instrument. Each wavelength adds a new layer of detail, revealing structures and processes that would otherwise be invisible. The future of galaxy observation is bright. In addition to the telescopes already mentioned, there are plans for even more ambitious projects. The Vera C. Rubin Observatory, named after the astronomer who discovered evidence for dark matter, will survey the entire visible sky every few nights. It will discover millions of new objects and track how they change over time. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will have a field of view 100 times larger than Hubble's. It will map hundreds of millions of galaxies and study dark energy with unprecedented precision. And in the more distant future, there are concepts for telescopes on the far side of the moon, shielded from Earth's radio interference. There are proposals for space-based arrays that could detect gravitational waves from merging supermassive black holes. There are even ideas for telescopes that could image the surfaces of planets around other stars. Each of these projects will add to our understanding of galaxies and the universe. Each will answer some questions and raise others. And each will remind us of how much we still have to learn. I want to pause, hear, and reflect on something. We have talked a lot about numbers and facts, about trillions of galaxies and billions of light years. But there is another dimension to this story that is harder to put into words. Looking at the universe fills me with a sense of awe. It is not just the scale that is impressive, though that is certainly part of it. It is the beauty, the complexity, the sheer improbability of it all. Think about it. The universe did not have to be beautiful. It did not have to be comprehensible. It could have been a chaotic mess with no patterns, no structures, no laws. But instead, it is elegant and orderly, with galaxies and stars and planets, with physics and chemistry and biology. Somehow, out of the raw stuff of the Big Bang, all of this emerged. Stars formed and exploded, seeding the cosmos with heavy elements. Planets formed, and some of them harbored life. And on at least one planet, that life became intelligent enough to wonder about its origins. We are the universe looking at itself. We are made of atoms that were forged in the hearts of stars. We are connected to the cosmos in the most literal way. And that connection gives meaning to our lives, even if the universe itself is indifferent to our existence. This is not a religious statement. It is a scientific one. The same atoms that make up our bodies are found in every galaxy in the universe. The same laws of physics that govern our world govern the most distant quasar. We are part of something much larger than ourselves, something that spans billions of years and trillions of galaxies. That perspective can be comforting or overwhelming depending on your temperament. Some people find it frightening to feel so small. Others find it liberating. I think both reactions are valid. The universe is big enough to contain all of our emotions. What matters, to me at least, is that we keep looking. Keep asking questions. Keep pushing the boundaries of what we know. That is what makes us human. That is what connects us to all the curious minds who came before, from Galileo to Hubble to the astronomers of today. And who knows what we will discover next? Maybe we will find a 10th planet in our solar system. Maybe we will detect signals from an alien civilization. Maybe we will figure out what dark matter is or why the universe exists at all. The possibilities are endless, and every discovery opens new doors. So the next time you look up at the night sky, remember that you are seeing just a tiny fraction of what is out there. Beyond those visible stars lie trillions of galaxies, each one a universe unto itself. And beyond those galaxies, beyond the edge of what we can see, lies even more, perhaps infinitely more. We are explorers on the shore of a cosmic ocean. We have dipped our toes in the water and marveled at its vastness. But we have only just begun. The journey continues, and the best discoveries are still ahead. Now let me bring this all together with some final thoughts on what we have learned and what it means. We started with a simple question: how many galaxies are there? The answer, as we have seen, is far from simple. It depends on what you mean by a galaxy, what part of the universe you are counting, and what tools you are using to count. The best current estimate for the observable universe is about 2 trillion galaxies. That number includes all the galaxies that have ever existed, from the tiny dwarf galaxies of the early universe to the giant ellipticals of today. It includes galaxies that have merged and galaxies that still exist. It is a kind of cosmic census, a count of all the star cities in our neighborhood of reality. But 2 trillion is just the beginning. The observable universe is only a small part of the total universe. Beyond the cosmological horizon, there could be many more galaxies, perhaps an infinite number. We will never know for sure because that realm is forever beyond our reach. But based on what we know about physics, there is no reason to think the galaxies stop at the edge of our view. So the true answer to how many galaxies there are might be, we do not know, and we may never know. It could be 2 trillion, it could be 200 trillion, it could be infinite. The universe is under no obligation to be small enough for us to count. This uncertainty is not a failure of science, it is a testament to the vastness of reality. Science has taken us from thinking the universe was just the Earth and a few thousand stars to knowing it contains trillions of galaxies. That is an astonishing achievement. If the final answer remains out of reach, that just means there is more to explore. Let me also say a few words about what galaxies mean for the possibility of life. With 2 trillion galaxies, each containing billions of stars, the number of potential habitats for life is staggering. Even if life is rare, even if only 1 in a billion planets develops life, there could still be billions of living worlds scattered across the cosmos. We do not know how common life is. We only have one example here on Earth. But that example shows that life can arise from non-living matter and evolve into complex, intelligent forms. If it happened here, it can happen elsewhere. The search for extraterrestrial life is one of the great quests of our time. We are looking for biosignatures in the atmospheres of exoplanets. We are listening for radio signals from distant civilizations. We are exploring the moons of Jupiter and Saturn where liquid water might harbor microbial life. So far, we have found nothing definitive. But the search has only just begun. The universe is vast, and we have only explored a tiny fraction of it. The absence of evidence is not evidence of absence, especially when we have barely started looking. If we do find evidence of life beyond Earth, it will transform our understanding of our place in the universe. We will know that we are not alone, that the cosmos is not just dead matter spinning through the void. Life will be a universal phenomenon, something that happens wherever conditions allow. And if we never find evidence of life, that would be significant too. It would suggest that life is incredibly rare, perhaps unique to Earth. It would make our planet and our species even more precious. Either way, the search is worth it. Let us also consider what the vastness of the universe means for the future of humanity. Right now, we are confined to one small planet. We have sent probes to other planets in our solar system, and we have landed humans on the moon. But we have never traveled to another star, and the distances are so vast that it might take thousands of years to do so. Yet the universe is old, and time scales that seem impossibly long to us are nothing compared to the age of the cosmos. The universe is about 14 billion years old. It will continue for trillions of years before the last stars burn out. On that time scale, even the most ambitious space travel becomes imaginable. Perhaps in the distant future, descendants of humanity will spread across the galaxy. They might colonize other star systems, build civilizations on other worlds, and explore the Milky Way. They might even someday travel to other galaxies, or perhaps we will remain confined to Earth, never expanding beyond our home planet. Perhaps we will destroy ourselves, or fade away, or evolve into something unrecognizable. The future is unknown, and we cannot predict what will happen over millions or billions of years. But thinking about those possibilities is part of what makes this topic so fascinating. The universe is not just a backdrop for human history. It is a stage that will continue long after we are gone. And the stories that unfold on that stage will be shaped by the same physics that shaped the galaxies we see today. Now, I want to address something that might be on some people's minds. Does talking about trillions of galaxies make Earth seem unimportant? Does it diminish the significance of human life? I do not think so. Significance is not about size. A painting is not less meaningful because it is smaller than a mountain. A symphony is not less beautiful because it is shorter than a river. Value is not measured in light years or solar masses. What makes Earth special is not that it is big or central. It is that it is home to life, to consciousness, to love and creativity and wonder. As far as we know, those things are rare in the universe. Most of the cosmos is empty space, cold and dark and lifeless. The places where something interesting is happening are the exception, not the rule. Earth is one of those exceptions. It is a tiny oasis of complexity in a vast desert of simplicity. And that makes it precious beyond measure, regardless of how many galaxies exist. At the same time, knowing about all those galaxies can expand our sense of possibility. It reminds us that we are part of something much larger than ourselves. It connects us to the cosmos in a way that is both humbling and inspiring. And it opens our minds to the idea that there might be other places, other beings, other stories unfolding in the vastness of space. That is not a threat to our significance. It is an invitation to a larger story. Let me also talk about the limits of our knowledge. Throughout this video, I have presented facts and numbers as if they were certain. But in reality, almost everything we know about the universe is provisional. It is the best understanding we have right now based on the evidence available. But new evidence could change the picture. The history of astronomy is full of revisions. We used to think the Earth was the center of the universe. We were wrong. We used to think the Milky Way was the only galaxy. We were wrong. We used to think the universe was static and eternal. We were wrong about that too. Each revision brought us closer to the truth. But there is no guarantee that our current understanding is the final word. Future discoveries might reveal that the number of galaxies is very different from 2 trillion. They might show that dark matter is not what we think it is. They might even overturn basic assumptions about physics. This is not a weakness of science. It is its greatest strength. Science is self-correcting. When new evidence contradicts old theories, the theories change. That is how progress happens. And it means that our understanding of the universe will keep improving as long as we keep looking and keep questioning. So take the number 2 trillion with a grain of humility. It is our best estimate today. Tomorrow, it might be different. And that is okay. That is how knowledge grows. I also want to acknowledge the many scientists whose work made this knowledge possible. From Galileo and Newton to Hubble and Rubin, countless individuals have contributed to our understanding of the cosmos. They built the telescopes, made the observations, developed the theories, and tested them against reality. Science is a collective enterprise. No single person could have figured all of this out alone. It took generations of effort across many countries and many disciplines. And it continues today with thousands of astronomers around the world working to push the boundaries of knowledge. Those astronomers are not doing it for fame or fortune. Most of them will never be household names. They do it because they are curious, because they want to understand the universe. because they feel the same sense of wonder that you and I feel when we look up at the night sky. That spirit of curiosity is something we should celebrate and nurture. It is what drives discovery. It is what makes us human. And it is what connects us to every other thinking being who has ever looked up at the stars and wondered. Now, as we near the end of this journey, let me offer some perspective on why this topic matters. You might be wondering, so what? So there are trillions of galaxies. How does that affect my daily life? In one sense, it does not affect your daily life at all. You still have to go to work, pay your bills, and deal with all the ordinary concerns of being human. The number of galaxies in the universe has no bearing on any of that. But in another sense, it affects everything. Knowing about the vastness of the universe changes how you see yourself and your place in the world. It provides context for the human experience. It reminds you that your problems, however real and important they are small compared to the scale of existence. That perspective can be freeing. It can help you let go of petty concerns and focus on what really matters. It can inspire you to live with more wonder and less fear. It can connect you to something larger than yourself, something that will endure long after you are gone. At the same time, the vastness of the universe can inspire action. If we are alone in this part of the cosmos, then we have a responsibility to preserve and protect what we have. If life is rare, then Earth becomes even more precious. The choices we make today will shape the future of life on this planet and possibly beyond. So the number of galaxies matters, not because it changes your mortgage payment, but because it changes how you understand reality. And understanding reality is one of the most important things a human can do. We live in an age of unprecedented knowledge. Never before have humans known so much about the cosmos. We have mapped the cosmic microwave background, the afterglow of the Big Bang. We have detected gravitational waves, ripples in space-time caused by colliding black holes. We have photographed the shadow of a black hole 6.5 billion times more massive than the Sun. These achievements are the result of centuries of effort and ingenuity. They represent the best of human civilization, and they are just the beginning. The universe still holds countless secrets, waiting to be discovered. Why does the universe exist at all? Why is there something rather than nothing? These are questions that science cannot fully answer, at least not yet. But by studying galaxies and the cosmic web, we can piece together the story of how everything came to be. In the beginning, there was the Big Bang, not an explosion in space, but an explosion of space itself. In a fraction of a second, the universe went from an unimaginably hot and dense state to something much larger and cooler. That expansion has continued ever since, and it is still happening today. In the first few minutes after the Big Bang, the building blocks of matter were created. Protons and neutrons formed from quarks. Those protons and neutrons combined into the nuclei of hydrogen, helium, and a tiny bit of lithium. The heavier elements did not exist yet. They would be forged later inside stars. For about 400,000 years, the universe was so hot that atoms could not form. Electrons could not stick to nuclei because they were constantly being knocked loose by energetic photons. The universe was a glowing fog, opaque to light. Then, as the universe cooled, something magical happened. Electrons finally joined nuclei to form neutral atoms. The fog cleared and the universe became transparent for the first time. The light that had been trapped suddenly streamed freely through space. That ancient light is still around today. We call it the cosmic microwave background, and it is one of the most important pieces of evidence for the Big Bang. After the universe became transparent, there was a long period of darkness. No stars had formed yet. The universe was filled with gas, mostly hydrogen and helium, drifting in the void. Gravity slowly pulled the gas together, forming denser and denser clumps. And eventually, in the densest regions, the first stars ignited. Those first stars were giants. They burned hot and bright and lived fast. Within a few million years, they had used up their fuel and exploded as supernovae. Those explosions spread heavy elements into space and triggered the formation of new stars. Generation after generation, stars lived and died, each one adding more elements to the cosmic mix. The first galaxies formed around the same time as the first stars, or maybe slightly after. They were small and irregular, nothing like the grand spirals and ellipticals we see today. Over billions of years, they merged and grew, consuming each other and building up mass. The cosmic web took shape, with galaxies clustering along filaments and voids opening up between them. That process of growth and merger continues to this day. Galaxies are still colliding and combining. The Milky Way is still absorbing smaller galaxies, and in the far future, the Milky Way and Andromeda will become one. All of this happened because of gravity and time. Gravity pulled matter together. Time allowed the process to unfold over billions of years. No designer was needed, no guiding hand, just the laws of physics operating across the vastness of space and time. That is the story of the universe in a nutshell, from the Big Bang to the cosmic web to the trillions of galaxies we see today. It is a story of creation and destruction, of order emerging from chaos, of complexity arising from simplicity. And we are part of that story. Our atoms were forged in stars that exploded billions of years ago. Our planet formed from the debris of earlier stellar generations. Our species evolved over millions of years, developing the intelligence to look up at the sky and ask where we came from. That is perhaps the most remarkable thing of all. The universe has produced beings capable of understanding their own origins. We are not just passive observers, we are the universe trying to understand itself. Some people find that thought humbling, others find it exhilarating. I think it is both. We are small and brief, but we are also connected to something vast and ancient. We carry the history of the cosmos in our very atoms. Now let me mention a few more fascinating details about galaxies that we have not fully covered. One of the most interesting is the variety of structures within galaxies. We have talked about spiral arms and central bulges, but galaxies also have other features. Many galaxies have bars, elongated structures of stars and gas that run through the center. The Milky Way has a bar, though we cannot see it directly from our position inside the galaxy. Galaxies also have halos, spherical regions of old stars, and globular clusters that surround the main body. The halo of the Milky Way extends far beyond the visible disk, containing some of the oldest stars in the galaxy. And then there are the streams. These are long, thin trails of stars that wrap around galaxies. They are the remnants of smaller galaxies that were torn apart by gravity. The Milky Way has several streams, including the Sagittarius stream and the Monoceros ring. These streams are like cosmic fossils, recording the history of past mergers. Another fascinating feature is the galactic wind. Some galaxies blow out huge amounts of gas from their centers, driven by supernova explosions or the activity of supermassive black holes. These winds can extend thousands of light years into intergalactic space, carrying material away from the galaxy and potentially enriching the surrounding environment. Galaxy clusters also have interesting structures. The space between galaxies in a cluster is not empty. It is filled with hot gas called the intracluster medium. This gas is incredibly hot, millions of degrees, and it glows in X-rays. In fact, the intracluster medium contains more mass than all the galaxies in the cluster combined. Clusters also contain dark matter, far more than visible matter. The dark matter provides the gravity that holds the cluster together. Without it, the galaxies would fly apart. We cannot see the dark matter directly, but we can detect it through gravitational lensing, the bending of light from background galaxies. These details remind us that galaxies are not simple objects. They are complex systems with many interacting parts. Understanding them requires studying everything from individual stars to the largest structures in the universe. Let me also mention a few of the biggest questions that remain unanswered. Despite all we have learned, there is still so much we do not know. What is dark matter made of? We know it exists, and we know roughly how much there is. But we do not know what particles make it up. Physicists have proposed many candidates, from WIMPs to axions to primordial black holes, but none have been detected yet. What is dark energy? This is even more mysterious than dark matter. We know it is causing the expansion of the universe to accelerate, but we have no idea what it actually is. It might be a property of space itself, or it might be something completely different. How did the first stars and galaxies form? We have models and simulations, but the details are still fuzzy. The James Webb Space Telescope is helping to fill in the gaps by observing the earliest galaxies directly. But there are still surprises, like the unexpectedly large and bright early galaxies that have already been found. Is there life elsewhere in the universe? With trillions of galaxies and countless planets, the probability seems high, but we have no direct evidence yet. Finding that evidence, even a single microbe on Mars or Europa, would be one of the greatest discoveries in history. These questions drive scientific research. They motivate astronomers to build bigger telescopes and develop new techniques. They inspire generations of students to study physics and astronomy. And they remind us that the adventure of discovery is far from over. As we close, I want to leave you with one final image. Imagine zooming out from Earth, past the Moon, past Mars, past the outer planets. Imagine continuing outward, past the edge of the solar system, into the vast emptiness of interstellar space. Imagine zooming out further until the Milky Way shrinks to a spiral of light, then to a dot, then to nothing. Imagine continuing until you can see the local group, then the Virgo cluster, then the Laniakea supercluster. Imagine zooming out until you can see the cosmic web itself, the vast network of filaments and voids that fills the observable universe. From that perspective, 2 trillion galaxies would look like grains of sand on an endless beach. Each grain contains billions of stars and countless worlds. And beyond the edge of what you can see, there is more, perhaps infinitely more. That is the universe we live in, vast beyond comprehension, beautiful beyond description, mysterious beyond understanding. And it is ours to explore, for as long as curiosity drives us forward. Thank you for taking this journey with me. The cosmos awaits. We have come so far in our understanding of the cosmos, from thinking the Earth was the center of everything to knowing we are one small planet orbiting an ordinary star in one of 2 trillion galaxies. That shift in perspective is one of the greatest intellectual achievements in human history. And yet, for all we have learned, the universe still holds countless secrets. Dark matter remains invisible and unexplained. Dark energy continues to push the cosmos apart for reasons we do not understand. The origin of life, the possibility of other civilizations, the ultimate fate of the universe itself, all of these mysteries await future discoveries. Perhaps the most profound lesson is this: the universe does not owe us answers. It is not designed for our convenience or our comprehension. And yet somehow we can understand it. Somehow beings made of atoms can figure out how atoms work. Somehow creatures living on one small planet can map billions of light years of space. That is the miracle of consciousness and curiosity. We are the universe becoming aware of itself, asking questions, seeking answers, marveling at its own existence. That capacity for wonder is perhaps the most precious thing in all of creation. So the next time you step outside on a clear night and look up at the stars, remember what you are really seeing. Each star is a sun, some with planets of their own. Beyond those visible, stars lie billions more that your eyes cannot detect. And beyond our galaxy lie trillions of other galaxies, each one a vast city of stars stretching across unimaginable distances. You are looking at infinity, or something so close to it that the difference does not matter. If you enjoyed this exploration, please take a moment to like this video and subscribe to the channel. Your support helps us make more content like this, exploring the wonders of the cosmos and the mysteries of existence. I would also love to hear from you. Leave a comment below and tell me what you think. Do you believe the universe is infinite? Do you think there is life in some of those trillions of galaxies? What question about the cosmos would you most like answered? Thank you for watching, and until next time, keep looking up at the stars. They have so much to tell us.